going on? It's Mr. Gust, and I'm back in the physics classroom today. I know I said physics classroom, but today we're going to talk about atoms a little bit because atoms are going to help us understand what charges do in conductors and in insulators. And if we're going to talk about ways of charging and electrostatics, the first thing we have to do is talk about our two primary categories of objects that we can charge, and those are conductors, those are insulators, those are made up of atoms. Let's talk about the atom. The atom is something we learned about in chemistry, but it does hold the fundamental charges that make up our universe. The atom looks like this. Inside the very positive nucleus, there are two kinds of charges. We've got the proton and we have the neutron, and outside, way more outside than I can possibly draw, we have the electron sitting in its orbital shells out there around the nucleus. Is this a good picture of an atom? Of course not. I haven't enough time to draw a Schrodinger model of this atom, but I can tell you this. The nucleus contains protons. Those things are the positive charges. They are in the nucleus. They have neutrons. Those things are neutral. That's how they got their name. These electrons well outside the nucleus, so far away from the nucleus we can't even see it. I can't even draw a representation that would be matching of their distance. These are electrons, and they are negatively charged. Now, ask yourself two questions. One, what do you think holds the electron in its position relative to the nucleus? What is in this atom that holds an electron there? You should have learned that. In chemistry, you should learn that protons are attracted to electrons. They are attracted to each other. Therefore, the electrons are held there. Now, a more challenging question that I'm going to ask you to do a little research on in your packet is, what keeps the protons in the nucleus? There aren't electrons in the nucleus. There's this densely packed collection of protons, sometimes upwards of 100 protons inside this nucleus. If that's true, why aren't they just exploding everywhere? Better yet, what happens when a nucleus finally does explode? Is there a lot of energy or a little bit of energy? This leads us to our discussion, right? Which of these particles are more freely able to move? Which particle requires less energy to move? Is it the electron or is it the proton? Well, we don't necessarily see protons flying around like crazy, leaving atoms, but we have an entire course in high school devoted to the movement of electrons. We call that chemistry. The movement of electrons happens relatively easily for some atoms. So when I think about which particle is the particle that moves from atom to atom or can move easily around an atom even, the electron is that particle. So if electrons move within a particle, we see spectra or emission lines forming and whatnot, but sometimes they move in a different way. So first note is that electrons are, quote unquote, relatively easily moved. Second note, protons are not. If you start drawing protons moving around, I'm going to walk by and boom! Nuclear bomb. No protons should be moving. Let's look at an example of what a conductor does. Conductors are things like metals, things that are made of objects or materials on the left side of the periodic table, things that typically have metallically bonded things. This is my Van de Graaff generator wand, but the tip of it, the head of it, is made of metal. Metals are bonded in a unique way where electrons freely flow between the metallic particles. It gives them the properties like their ductility and their malleability and their conductivity is because electrons move so freely. So when I think about an object that is made of metal and is neutral, an equal number of positive and negative charges, equal numbers of protons and electrons there. If it is neutral, like I see here, they are evenly distributed. But now, if I were to take this metal object and somehow polarize this object, I would need to indicate how I have moved particles throughout. So let's imagine I take, a negative wand and bring it over here and hold this negative wand near this charge. So I'm going to go ahead and draw my negative wand right here. It's very, very negative. I'm not going to touch it, but I'm going to bring those negative charges, those electrons, close to this object. what that will do in conductors is it will cause those electrons to flow away. Electrons easily move. Electrons flow away from this wand and end up as far away as possible from that source of electrons. Now notice, did my protons move? They better not have moved, because if those protons move, boom, we have a nuclear bomb. Those protons don't move. The electrons move freely in the conductors. Now, what's different from conductors and insulators is that insulators, let's go ahead and have an insulator like, I don't know, say something less metallic like a plastic ruler. Plastic rulers are things we'll use in class. They charge up nicely when you use friction to transfer electrons and charge between them. So we have this example. It's neutral, so let's go ahead and draw our neutral atoms here. And now these neutral atoms, they actually exist kind of like, I know I'm drawing them as charges, but they exist as atoms, right? These atoms have a partial positive, I'm not atoms as molecules really, but a partial positive side and a partial negative side of this molecule. So when I do something like, I don't know, bring my negative one really close to this ruler, it's not a conductor. Electrons do not move freely. When it comes to things that are like insulators, they are bonded in an ionic system, and that means those electrons are trapped and wrapped up in these covalent bonds. They don't move so freely. So what happens, instead of electrons totally moving, those molecules with itty-bitty partial positives and partial negative sides, they orient themselves in such a way so that the positive charges on the positive side of that molecule actually does flip. And I'm seeing myself with positive and negative parts of the same atom, or no, I keep saying atom, same molecule, flipped towards. Now, it's not a flow of positive charge and a flow of negative charge. It's just a shifting of the orientation of the molecules in that substance near that. What is the difference? Electrons in conductors flow easily. Electrons in insulators do not. What is the difference? Electrons are moving across an object in a conductor. Molecules are orienting or reorienting themselves slightly in an insulator. How do we know this? Because we know electrons move easily and protons do not. There's a couple more questions on the intro to electrostatics in the beginning of your packet. Go answer those. As always, if you have questions, you drop it in the comments, you send me an email, you ask me in class. Until next time, see ya!